Hello, welcome to the second video lecture about lexical analysis, where we'll talk about how to use regular expressions in order to define tokens in our programming language. As we saw before, a regular language is constructed by using these three operations. So you can use concatenation, you can use union of two regular languages, and then there is a concatenation on steroids, which is concatenation star or Kleene closure, where you can repeatedly concatenate strings from a language. So these three operations use the base case, which are just the language containing just the symbols of the alphabet, and construct new regular languages from those basic elements. So each regular language is just an example of a formal language. So regular languages are a specific kind of formal language. And a formal language is nothing but a set of strings. So a regular language can be finite. So this is an example. R1 is a finite regular language, only has one string. It can also be infinite. So R2 is an infinite set of strings, which is defined by all the A's of length greater than 1. So you have A of length 1, 2 A's, 3 A's, etc. So each of the elements in this set of regular languages is itself a regular language. So R here is a set where each element is a set of strings, potentially an infinite set of strings. So you can see here that if I look at a set of strings like this, Bn, where n is greater than or equal to 0, I can look at this set of strings and I can also construct a regular expression for this set of strings, right? So this would correspond to the regular expression B star. So what we can do is make an equivalence between regular expressions and regular languages. So when we define at a high level what we need from a set of strings, we can then write it down as a regular expression. So the way to make this equivalence explicit is to create a meaning function. We'll call it L of R. Informally, you can also think of it as language of R. And it's a meaning of this regular expression, which is exactly equal to the regular language for that regular expression. So let's take an example where the regular expression we have is A star, then L of A star, or the language of A star, or the meaning of A star here is the set of strings. So what we're taking is, we're taking this specialized syntax, which is A followed by the asterisk star, and interpreting it and giving it a meaning of this infinite set of strings, which is the empty string, 1A, 2A's, 3A's, etc. So as you can see, we can take a regular expression and map it. So a regular expression is nothing but an ASCII sequence of characters, and we're mapping it to this meaning, which is a set of strings. Meaning of the empty regular expression is just the empty string. So we don't typically use this. The empty string has its uses, as we will see, but we don't typically want to match an empty string. So we never really use this ability, but we need it to be mathematically general. L of A is just a set containing A. So any symbol from the alphabet can be a single element set, and that would be, then you can take R1 and R2, two different regular expressions. So this is a string R1 with a bar, a pipe, and an R2. So that stands for alternation, or R1 or R2 is the way you read it. And the way that we can construct a meaning out of that is to take the language of R1 and the language of R2, and then take the union of those two. Right? So if I have A or B and I want to take the meaning of that, then I would take the language of A union with the language of B, which is nothing but A union B, which is AB. Concatenation works in the same way. You can take R1 and put R2 immediately after it. And you can construct a set of strings by taking every string from R1 and then concatenating it with every string from R2, right? So if I take the language of AB is just going to be the language of A is just A concatenated with language from B, right? So what I end up with is this set which contains B concatenated to A. I can also do iteration, or so I can take R1 and repeat it many times. This is exactly the same operation as that, right? So that's just the same as saying L of AA is equal to, pretty straightforward. It's just a concatenation, except you're repeating the same regular expression. And finally, you can take R1 star, which is the 0 or more repetitions of R1, and it's done in the same way that we defined a regular language, which is you take the L of R1 0, so this gives you the empty string, union all the one length strings from R1, or one length repetition, sorry, could be actually longer strings. If R1 defines like a string of length 3, then it would be one repetition of that string, and then 2 repetitions, and then 3 repetitions, and so on. So this creates a set of strings which we define as R1 star. So as you can see, this would be an example of taking A star and then converting it into a regular language for A star. So when we want to define patterns for the different tokens that we have to define in our programming language, we can now look at the specification and use a regular expression now to represent that specification. It's almost like an executable specification. So an integer can be defined. So let's say in our programming language, we are defining it as a non-empty sequence of digits. Then I can write down this expression, which is 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. And this alternation gives me a single digit. And then I can take a digit followed by 0 or more repetitions of a digit. And I can represent that as digit plus. So plus is this special sort of extra symbol which is not really core, because I can represent it simply using star and a single sort of regular expression of digit. So by combining these two, I can get the definition of digit plus. An identifier, let's assume that the identifier has in our language specification a definition that says it's a sequence of letters or digits and it has to start with a letter. I can write it down as the sequence of digits from 0 to 9. So if I go back here, notice that this is a tedious way to write all of the digits from 0 to 9, and I can write it more concisely as this sort of character class, so 0, 1 through 9. These two are equivalent. So this is just, again, syntactic sugar for this alternation here. So in this case, I would get a digit is just this character, any of these characters from 0 to 9. I can do any letter, uppercase or lowercase, from A to Z, and that's a letter. I define this as sort of a letter. And then I can take an identifier definition as starting with a letter. So it starts with a letter, and then it's followed by a letter or a digit, right? So you can have a letter or a digit, and then I can put a bracket around this, and then I put a star here, which says I can have 0 or more repetitions of a letter or a digit, as many repetitions as you want, including the empty string. So this covers identifiers that look like A, B. You can also have A1, B2, etc. So you can have identifiers of any length here. So you don't have to, and this, as you can see from examining this regular expression, you can map it to this definition that we want. You can define white space as a non-empty sequence of blanks, new lines, and tabs. So I can write a blank here, which is just a space, and tab and a new line. Now, it's the interesting thing here is I'm defining a tab and a new line, which is a white space character using a sequence of 2 characters. So this is a backslash, and this is a T. So that's actually defined using 2 characters, a backslash and a T, instead of literally putting a tab character in it, right? So if I have, again, the same way here, this is 2 characters, backslash and N. If I were to physically insert a new line, it might look something like a Control M character. That would be single character. This would be, and this is 2 characters. So I'm using this representation of backslash n to represent the new line. So this equivalence is done when I interpret this regular expression. So this is very similar to what we saw happens in a programming language from the intro slides. If we want a pattern definition for numbers, which includes all kinds of numbers like floating point numbers, etc., then we want to write down this regular expression. We start with a digit, which is any number from 0 to 9. We have digits, a new sort of variable, which is 1 or more repetitions of any digit from 0 to 9. And then we can put an optional fraction, which has a dot followed by digits. So you can any number of digits. And then this question mark operates over this entire sequence and says that you can have, it's optional. So you can have one of these and that's it. Or you can have none of these. So that's what the question mark means. The opt exponent. So if I wanted to do e of minus 12 or e of plus 10, then this sequence would represent that kind of string, right? So again, it's optional. So I can have it. I can have one of them, or I could have none of them, right? So I could have a number like 2.3, or I can have 2.3 e plus 12. So this part is optional, which is why we use a question mark to represent it in the regular expression. And then we have a number, which is defined as any number of digits followed by the sort of decimal part of it, the floating point part of it, and then optionally having an exponent. So this lets you define numbers that match all of these strings. So these are just strings at this point, right? They're not numbers yet. So these are strings in the programming language that we want to match with this regular expression and then map it to the appropriate number. So when you're writing these regular expressions, you should be familiar with all of the different sort of elements that you can use. Obviously, you have the core elements, which is concatenation, alternation, and star. Those are the main things. Those are the core operators. But there's a lot of useful operators like we saw. And by looking at the LEX definitions, looking at the LEX practice on the course website, you should get more familiar with all of the different ways of using regular expressions if you haven't already used them extensively. Before you can start using regular expressions to define the tokens of a programming language, you need to understand how a regular expression, a set of regular expressions can be used in order to match the strings. So we need to understand at a high level at least how a tool like Lex would do the matching for you, so that you understand when the matching will work and when the matching won't work. So the first task is to define a regular expression pattern for each token in your programming language. So you would write a sequence of regular expressions, one for each of the tokens that are defined in the programming language specification document. So you have int constant, which is defined as R1, R2 is a keyword, and R3 is an identifier. So this is obviously just a very simple example. You might have hundreds of tokens in your programming language, and you would write one regular expression for each token. Then you have to construct an ordered list, and we'll see why this list needs to be an ordered list. But it's important that it is an ordered list R containing all of the T regular expressions. So I'm assuming that there's some number T of regular expressions for the T tokens in this programming language. Once you've written down an ordered list of regular expressions for all of our tokens, let's see how we can use this in order to do the lexical analysis phase of the compiler. So I'm going to explain it using this example. And the input string is provided to us, which is just a sequence of symbols, x1, x2 to xn. So in this particular example, it's this input starting here, which is the start position, starts with that D character. And you can see it has a double followed by the numbers 1 and 2, followed by an equal to. So remember that we have this ordered sequence of regular expressions. R1 is recognizing integer constants, so it's not going to match the letter. So it doesn't get any matches. R2 is a regular expression for the double keyword in this programming language. So it matches all the way up to the first 6 characters. So it finds the keyword double, right? And then we have R3, which is the regular expression for identifier, and that matches all the way, including the numbers 1 and 2, because the definition of the identifier includes letter followed by letter or digit star, right? So it would match all the way up to there. And then there will be other matches for all the other tokens. So once we've matched all of them, what we would do is use this sort of strategy of maximal munch, where the longest match always wins. So if there's more than one matching regular expression, or in this case, the regular expression and the token mean the same thing, right? It's a regular expression for that token. Then we would return the token which has the longest match. And once we do that, we can see that we've matched all the way up to here in the input string. Then we set the next start position and we do this process all over again. So we're repeatedly taking the longest match that we can get for each token, and then we start from the next position and do the matching again and get the next token. So as a result, here we would get a token stream, right, for the first token and the next token and the next token until we are done reading the program string. Let's consider a case where the input is just double equals, right? So that's the start position again. So I've reset the start position back to the first character D. And now we do the same thing. We try to match R1, which is integer constant doesn't match, double matches, and then identifier matches. So both of these patterns are valid for this input up to this equal to. So you can see that double matches up to character 6 and identifier also matches up to character 6. In this case, obviously now we have a tie. We need to break this tie somehow. And the way that we do this is, remember I said it was important to have the list be an ordered list. And that's what we're going to use in order to break ties. We choose the regular expression that is earlier in the list. So the higher, essentially, earlier in the list means higher priority. In this case, it would return T double and not T identifier, right? So if two patterns match, always pick the higher priority one. And then we start from the equal to, right? So it could be, remember that we don't really care about syntax errors at this point. We just create a token stream. So in this case, the token stream would contain T double followed by T equals to, which would be this token for this equal to sign, and so on. So what happens now if no regular expression matches, right? So we saw this case where something was matching. What if we go through all of the tokens and none of them match? And that means that there is some kind of error in the input, because if we've done our job correctly and we've defined all the tokens as regular expressions correctly, then there must be something malformed in the input, and that's why none of the regular expressions match. So in order to deal with this case, we create a new error regular expression, and there might be actually more than one error regular expression that you might want. You might want a special one for, something which opens the double quote and doesn't close it, something which if you have multi-line strings, multi-line comments like this, then if these characters are missing, you might want to create an error regular expression that's specific to that kind of error. But the easiest thing to do is to have a regular expression that matches any input, and that regular expression should be the last in the list. So it always matches, right? But it matches with the lowest priority. So if anything else matches, it would prefer that. But if nothing else matches, then it's a kind of token that would collect everything and say, oh, this must be an error. So when it matches, we know that there was a lexical analysis error, and we report that error to the programmer. So when we're writing this compiler, we want to catch these lexical analysis errors and report them. Here's a pseudocode for the process that we just talked about. You don't really have to go through it in detail here in the video lecture. I encourage you to go through the pseudocode just to make sure that you understand the notation. But the main thing I'll say is that it's returning a list, which is the stream of tokens, a list of tokens that comes out of the lexical analysis phase. And for all of the regular expressions, it's matching it. And when it matches each regular expression, it stores all of the matchings in this sort of list of matches here. And then it finds the maximum match that you can get. And you would record both what the maximum match was and which token that corresponds to. And then once you have that, you just record that, and then you set the new start position and then repeat. So rinse and repeat until you get to the end of the input. So when you reach the end, what the output you get is a sequence of tokens. So token 1, token 2, token 3, and so on until token k. So obviously k is going to be somewhat less than n, because presumably you have most tokens will be greater than length 1. Some will be length 1, but not all. In this phase where you're taking the max, you would have to insert some kind of logic in that max function that would choose the smallest m value, the higher priority regular expression, and thereby break ties with which have the same length. So in this video, what we've seen is how we can use regular expressions for lexical analysis. And regular expressions are a nice, convenient, concise notation for string patterns, which we can exploit. So instead of writing very large loop and switch scanners, you can define each of your tokens independently in a modular way and use regular expressions to say this token corresponds to this regular expression, etc. and you can map that definition of a token back to the pattern that's mentioned in the language specification. So you can look at the regular expression and say, does this capture the language specification or not? And once you have that, as we'll see, there are algorithms that will take the regular expression and then convert it into a matcher for you, right? So you don't have to write the matching code, because the regular expression can essentially be converted into the code that can match strings for that regular expression. So what we saw in this lecture is that using regular expressions in lexical analysis requires some small extensions. You need to always pick the longest match, and that's a convenient way to decide which token you're going to return. It's always the one with the longest match. If you have ties, we use a priority ordering among the different token definitions, among the different regular expressions, to say, okay, if many of them have a matching for the same length, then pick the one with the higher priority. And we need to handle errors, because a good compiler should always return good error messages to make it easy to use. A good algorithm for lexical analysis. So far I've given you sort of high-level pseudocode. So if you implement this correctly, you should require only a single pass. There should be no backtracking. And there should be typically a few operations per character. Then you can avoid writing a big loop and switch scanner. Instead, use this much more modular way to define a lexical analyzer. Now, so far what we've seen is how we can write down regular expressions for tokens. Next, we'll look at how do we take these regular expressions and implement a tool. So we'll be using a tool called LEX in our first homework to define the lexical analyzer for a programming language. Now, how does LEX work? What are the algorithms that go into writing a tool like LEX? That's what we'll look at next time.